First we got low rank fine tuning with LoRa, now we got low rank training with GaLore. So you've probably heard about GaLore, and it is essentially a way to train an entire model using low rank or using a low rank method, as opposed to just fine tuning one with something like LoRa. This also works with fine tuning as well, interestingly, and you can see here it does quite a good job. So here is the memory, and here is the method. So usually you use a floating point 16 or BF16, which is just a more stable version of floating point 16. And it has quite a bit of memory usage for training a Llama 7B. And this includes not just the model, but also the optimizer states. So if we go here, it says here that just storing the model alone requires 14 gigabytes for the trainable parameters alone. So if you store it in floating point 16, each parameter is 2 bytes. And here it's 42 gigabytes for the atom optimizer. So you need to store, well, your moments for the for the atom optimizer, and then 2 gigabytes for the activations. So quite a bit for both BF16. Add a factor is a method to kind of reduce that, and 8-bit reduces it even more. But they have a massive reduction in terms of memory using 8-bit GaLore. Even between the 8-bit method is quite crazy, and you can actually add it, make it even lower with add a factor. So quite interesting that you get such low memory usage, and the results are very similar. So yeah, that's the idea. Let's get into GaLore. So I would go into how LoRa works, but this method is very different from LoRa. LoRa is a way to fine tune a model. So if you already have a model which was trained on some data set, you want to find, and it was trained on some big data set. You want to fine tune it on some smaller data set. LoRa would just fine tune this model on this small data set to put it in on some downstream task. In this case, you want to completely train it using the data. So no fine tuning. LoRa can kind of do that, but also not really. It's not that good at it. So yeah, GaLore. So the first thing is kind of the intuition behind that. They have some proofs, and it's very nice that they have proofs in this case. Or it's always nice whenever there's proofs, but that in this case they have a lot of proofs showing that this is provably going to converge with high probability. So let's go into that. So the first thing they want to prove is that there exists something that's low rank. And in this case, they say that the weights are not low rank. So they say that over here somewhere. They say that basically the weights are not low rank. So let me find that. So right here, for pre-training from scratch, it is shown to require full rank model training as a warm-up before optimizing in the low rank subspace. So you need this full rank. You need full rank weight matrices, and you just need them for warm-up. But they basically say, oh, if you need a full rank matrix, then you can't really get your low rank approximation even from the beginning of training. So instead of using low rank weight matrices, they use low rank gradient matrices. So they say, our key idea is to leverage the slow changing low rank structure of the gradient of the weight matrix rather than trying to approximate the weight matrix itself as low rank. So that's the big idea. They're not trying to, so LoRa basically breaks up the weight matrix into two smaller matrices, making it low rank. So LoRa basically has your weight matrix, and then you have your A and B matrix. Here you have your weight matrix, and each of these have their gradients. Here you have your weight matrix, and you have your gradient matrix. And the gradient matrix is going to be your low rank matrix. Your weight matrix is going to stay the same, while here your weight matrix is low rank. So that's the idea. And they have a proof. So the first thing they wanted to prove was that this does have a low, that the gradients are actually low rank. So that's the first thing they prove. Move this. So to kind of start this, they break up the gradient into the sum, or the weight into the sum of gradients. So your weight matrix at basically the end of training is equal to your initialized matrix here, plus your learning rate, times the sum of all the gradient matrices here. So this here would just be your gradient matrix at some time step, or at a time step. So this would be like your gradient at time 0, time 1, time 2. And P of t is some function that regularizes the gradient. So you can think of this as atom, and this is just the gradient that's put into the atom optimizer to regularize the gradient and make it converge better, or make your model converge faster. And this is just the sum over all the gradients. So you can basically decompose your weight matrix into this. This is equivalent. This is just an equivalent representation. And yeah, so in this case, P sub t would be your atom optimizer. Your atom optimizer has two parts, exponentially moving averages of the momentum. So this is just exponentially moving average of your gradient. And this is the exponentially moving average of the variance. And this is basically the formula to combine them. And this is what you're going to use to update. So this is the output of PT of GT. So yeah, that's just normal atom. Atom is just an example they use. They generalize, and that's why they put PT here instead of atom. This generalizes to every optimizer, which is nice. But they use atom because everyone uses atom. Yeah. So once they kind of have it in this formulation, they want to show that it is full rank, and they have a lemma here, or it's not full rank. It's low rank. Yeah. So they have a lemma here. The gradient becomes low rank during training, and they do prove this. They show that it does have that it does become low rank during training, specifically if you can write it out in this form. So gradient has low rank during training if the gradient can be decomposed into this form, where A is a constant matrix and B and C are positive semi-definite. So specifically, if you can get the gradient in this form, then it's provably low rank. So they work around this assumption here that the gradient is of this form, A minus B W C. So that means that the gradient is a function of the weight matrix and just of this general form. And then to update it, the assumption is you take the weight matrix and you just basic normal update rule, essentially. This is the more important assumption here, that the gradient looks like this, because they basically rely on that assumption throughout the rest of the paper. And one thing to mention is that this assumption is mostly valid. So if we look at this, they say that lemma 3.1, they assume a parametric form of the gradient, so just this. And they say that this is not a limiting assumption. It not only holds for a simple linear network with the simple MSE objective, but it also holds for more general nonlinear networks known as reversible networks. This is a second assumption that they're making, that you have something called reversible networks. And this is not as good of an assumption. So if we go down here to what a reversible network is, it's defined here. So a network that maps an input x to an output y is reversible if there exists a function k so that this is satisfied and the gradient satisfies this function here, where g sub y is the backpropagated gradient at output y. And here k depends on the input and the weight of the network n. So this is the assumption they're making, that there is reversibility and that you can represent the gradient as the formula above. This assumption isn't as strong because you have to have your function here be represented as some, so this is going to be like your ReLU function. So in this case, it would be like y is equal to ReLU of x. And I guess w, where this is just 0 or something like that, You can also think of this as like your linear layer as well, which would take an x and w. So these need to, there needs to be some representation, some function k, which satisfies these two properties here. The first property is that you have y is equal to k of x w times x. So this is the first equation that needs to be satisfied, and the second equation is g of x is equal to k transpose x given x and the weight matrix times the output gradient. So this is basically the output gradient, or this is the gradient of the output. So this is the gradient above this layer, and this would be the gradient of this layer. And you need to be able to represent what this is. So k is just some arbitrary function, and this is an assumption they're making. The assumption is that you can write your function as this. Really works that way. The linear layer works that way. They also show that softmax works that way. If I go up here, they show with this lemma it is clear for a reversible network. The gradient is the following form, and this is the softmax. So they can prove that it has that structure. So it has the A, B, C structure, and it's reversible network. So that's the assumption they're making. The assumption does not hold. They don't know if the assumption holds for attention. They say for architectures like self-attention, one possibility is to leverage GOMA to analyze how and they leave that to future work. From this property, it is clear that the resonant architecture works. So the resonant architecture works. It satisfies reversibility, but they are uncertain if the self-attention mechanism does. However, their method still works even if they make this assumption. So yeah, just something I wanted to note that they make this assumption before they or whenever they're defining their method. Nonetheless, the method still works quite well. There just may be some more proofs that need to happen. So yeah, if you can represent the gradient like this, it is low rank. So they basically prove that your gradient is low rank because you can represent it as this. And they leverage this property, they represent the gradient this way, and it allows them to leverage this low rank property of the gradient. So now that we have all the proofs out of the way, we can now assume that our gradient is low rank because they proved that. So how do they leverage this? The key idea is that you can make weight updates in this low rank space. So you can leverage this property to do your weight updates in a lower rank space because we proved that the gradient can be decomposed into a low rank space. So we have here, let me move this, remove this. And this is just your normal weight update. So your weight at time t is equal to your weight plus all the regularized gradients. And this is the important part. So your gradient, if we show above here, where are they? Right here, yeah. Your gradient is just a minus bw, or it's just normal gradient, what they proved. Here you can decompose it because we know it's now low rank into this. And this looks like a mess, but it's actually pretty simple. You have this inner part here. This basically projects it from a full rank to low rank. So this is a projection to low rank. And then you have your regularizer here. So this is so you regularize in low rank. So reg in low rank. Rank, and then you project back up into your full rank. So project into your full rank. So you basically project into some smaller space using this here, these functions here. You then regularize in the low dimensional space, and then you bring it back to the high dimensional space it was originally part of by just inverting P and Q. Yeah, and they have that here. They mentioned that. And essentially what this is doing, it's projecting your gradient to a low dimensional space. You do the regularization in the low dimensional space. And remember that we need to have our weights in full rank because the weights need to be in full rank. It's shown that they can't be low rank. So we project back to a full rank space, or to the original space, and then we can now add it to the weight matrix, because this is now in full rank space. So this is now in the full space. So it's the weights. So we're not doing anything to the weights. Weights are staying the same. The gradients are being projected. They're being updated and then projected back. So this is basically the formula here. Yeah. So now let's look at the code. So the idea is shown here, and then we'll get into the actual code. So basically, the intuition is for all the weights, we take the gradient of the weight. We then project into a low dimensional space. We update it using, say, atom. So this would be our atom step on the low dimensional space. And then we project back into our high dimensional space, and then we update the weight. So that's all we're doing. Project, update, project back. Now, the actual algorithm is here. So this algorithm also looks pretty complicated, but it's not that bad. Yeah, so not that bad. Specifically, they're using atom. So because everyone uses atom, so that's what they kind of show off here. But like I said, it can be used for any optimizer. So in this case, you initialize your moment, your first and second moments to 0 moments, and these are your first and second moments of the weight matrix. So now they have this algorithm here, and well, I guess before I mention that, I should also mention that, or some more intuition behind this before I go into the actual algorithm. There's a second thing they do. Instead of just projecting once to a low dimensional space, they project multiple times into a low dimensional space, and I feel like this image gives a pretty good intuition behind that. Yeah, sorry. So essentially the idea is, so this is like a 3-dimensional space here, some high dimensional space in a way. And let's say we have these planes that we kind of want to move on. So the planes are going to be our subspace in our high dimensional space for intuition. In reality, or you're going to have like some massive 1,000-dimensional space, and you're going to be projecting to like a space of like 100 or 10 or something like that. And that would be like your planes. So you're projecting to these subspaces in your high dimensional space. Now, this is our initialization, W0, and doing these updates, so doing this update a few times, I don't know how many times I'm going to circle that, but doing that update a few times is basically walking along this subspace in the high dimensional space. So this would be the first update, this would be the second update, the third update, and then the fourth update. And these are just updates to the gradient itself. So you're just getting the gradient and you're updating it in this low dimensional space. And you're adding it back to the weight matrix, which then becomes this here. So this is just a 4-step, or this is just 4 steps. Now, one thing they mention here is that they, is up here? Yeah, for a complex optimization problem such as an LLM or such as LLM pre-training, it may be difficult to capture the entire gradient trajectory with a single low-rank subspace, which is intuitive because you're just walking along this same space and you don't need to optimize it anymore up to a certain point. One reason is that the principal subspace of B and C may change over time. So they mentioned that, and they basically are saying that if you optimize the same subspace, it's once you've optimized it for long enough, you don't need to optimize that part anymore, and you should probably optimize a different part or a different subspace of your entire space. So they mention here that they allow GaLore to switch across low rank spaces. So when switching from the ith subspace step, we reinitialize the projection by performing SVD on the current gradient by equation 14. So yeah, the idea is that you're going to switch spaces, so you can see this is kind of like orthogonal to the old subspace, and then you walk along that path. So every so often, and then you work on that subspace. So every so often, you're going to switch subspaces instead of just working on this one subspace here. You're going to stop for a sec and then switch subspaces to another subspace and then start optimizing there. Yeah, so second part of GaLore. So instead of just doing this the whole time, you change your subspace. And they do that with a parameter, t, big T. which is just it's just a hyperparameter you tune. So every big T steps you switch. And I think they make it like 100 or something like that, like 50 to 1,000. So yeah, those are the two parts. Finally, you may be wondering, how do you actually do this this decomposition that they have here? And they do that with singular value decomposition, and they have the formulas here. So normal singular value decomposition. They say the theorem tells us that P and Q should project into the subspace corresponding to the first few largest eigenvectors of B and C for fastest convergence. So you basically want to find the highest eigenvectors for what they defined as B and C. So, and you do that using singular value decomposition, and you basically just take your P and Q and work with that. So you use SVD to collect the eigenvectors, and you just select the first R. So, and that's what we're going to see in the algorithm down here. So that's basically the idea. You just use singular value decomposition to project this to a lower space, essentially your weight matrix. So that's how you do this over here. This G, you just use SVD. All right, so now I can actually go into the algorithm. Sorry about that. So for the algorithm, you are going to repeat this. So this is your loop, your update loop, and this is going to be your update loop throughout all of training. And like I said, these here are your first and second moments initialized to random values, or zeros, or sorry, initialized to zeros, not random values. So the first thing you do is you get the gradient of your weight matrix. So yeah, gradient of your weight matrix for a layer. So, or for a function. So linear layer, whatever, just get your gradient here. Then what you're going to do, we'll go along this step first. So here, or rather, initially you're going to initialize your P matrix. So this is going to be our projection matrix into a lower dimensional space. And you do that using SVD. So you just do SVD of the gradient, and this gives you your matrix, which allows you to project to a low dimensional space and then back to it. And you just select the R highest, or the R, they mentioned it up here. It was the R highest singular values, I think, yeah. Or rather, the R most important eigenvectors. Yes, yeah, R most important eigenvectors for U or V. You may notice that they only use one U, or they only use P. And here they use P and Q. I'm erasing this. Here they use P and Q. We'll get to that in a second, but think of P as just a projection to a low dimensional space, and then you can get back by multiplying by the transpose. Yes, or rather, you get to the space multiplying by the transpose, and then you get back multiplying by the normal matrix. So this here just gives you your, just get the R most important eigenvectors, allowing you to project to this low dimensional space, and then you can use this to project back up. So this is your low rank projection, and you only update this every T steps. So you would update that here, so you get a new P here, and once you're done optimizing along this trajectory, once you get here, you then get another P, which allows you to go along a different subspace of your entire space. So yeah, you just update it every big T steps. Otherwise, you just stick with your old P, your old projection, because you're working on the same subspace. So once you have your subspace projection, you then project your gradient to the subspace. So R is your projected gradient in the subspace. Now, once you're now this is just step one. This is just your projection to low rank LR. Now, the second thing you do is you update your matrix using your optimizer, or using your regularizer, rather. So in this case, you have your moment updates, And here I think they actually got this part wrong, the notation a little bit wrong. I think this is supposed to be M and V hat. Same with here, because these are your corrected moments. The normal M and normal V should just store the moment updates. I could be wrong, but I think that they messed that part up. I'm not sure, but anyways, you update the moments with the projected gradient. So this is all in low rank, or this is all in the low dimensional subspace. And then here is going to be your gradient update. So in normal Atom, you do the exact same thing, or rather something similar, where you have your G, you update your M, and you have your new G. Instead, these are going to be low rank because you're working in your low dimensional space. So instead we have R, which is your low rank gradient, and N, which is your regularized low rank gradient. So this is just regularize. This step is update your weights. So you take this here, and this is project back into your high dimensional space. So you notice we have P here. This projected to the low dimensional space. This projects back. Alpha is if you've seen LoRa, alpha is basically how much does this gradient update. So in a way, it's kind of like a learning rate. How much does it actually update the weight matrix? And then you just multiply this by the weight matrix. So here, you update your weights using this new gradient, which was regularized in the low dimensional space and then projected back to the high dimensional space. And this is just your normal update rule here. And this is updating T, so that you know if you should update your projection or not. So that's all it is. It's get your projection every so often, project to the low dimensional space, update update in the low dimensional space, regularize, project back to the high dimensional space, and update your weights in the high dimensional space. Yeah, so that's the algorithm here. So in similar to LoRa, you have this R here, which basically tells you your low rank projection. In this case, this is the number of eigenvectors you're working with, the important eigenvectors you're working with. In LoRa, it was just the space you're. In both cases, it's the low dimensional space you're projecting to. That's it. Now, one thing I mentioned is that we only use one matrix. So in this case, we only use P. They mentioned down here why you do that. So to achieve the best memory performance trade-off, we only use one projection matrix, P or Q. So remember that our gradient was composed of both P and Q. So they use like partial SVD and only do one part of this. So, and we'll see why in a second, but they only use one projection rather than both projections. They project the gradient into P transpose G if M is less than N. So we have our formula here. Oh, and let me change this. And they go to GQ otherwise. So we have our formula, which is R is equal to B or P transpose G and Q. So if M is less than or equal to N, you project to this space. And if it's not, then you project to this space. So you're only using a half of the SVD for your projection. And this basically projects to, it's just a partial projection in a way. So this part or this part. Yeah, so that's all they're doing here. And it becomes evident why they do that whenever we look at the amount of memory it takes up. So if we look at the amount of memory it takes up here, let's go to LoRa. If we're doing training with LoRa in some way, then we need to store three things. We need to store the original weight matrix. This is just W. We need to store the B matrix and its moments. So this is B, the momentum and the variance, or the first and second moments. And we also need to store A, M, and V for the two moments of A. Now in this case, we only have one weight matrix. This is W. Now, we also have to initialize the two moments. So these are the two moments for W. And then a third thing we have to do is we look at this, and this is our P. This is our P matrix here. So it's a weird comparison, but they're different. Remember that we don't train W and LoRa, but only A and B. So the memory in this case is low. It's a lot lower by a good factor. 2 for MR for P. So it's only a third here, and it's 2/3 here. And like I said, these are your first and second moments. These two parts right here. And this is your P matrix that you're storing. So the reason they only do the partial projection instead of the full projection is because it's basically good enough, and you only have to store one. If you used both P and Q, then you would have to store P and Q here. So yeah, and this projects it to the low dimensional space. So Rn versus MR, where R is your low dimensional space in between M and R, or M and N. So hopefully that's clear that they only project they only use one half of this projection, so that they only store either P or Q, and so that you can either get to the MR space or the NR space, NR, depending on which one's lower, M or N. Yeah, so that's basically the intuition behind that. They mention, they mention that they only use one, and that's what you're storing here, your P. So you only have three things that you're storing: M, V, and P, and this is for Atom, the usual optimizer you're going to use. Unlike LoRa, which has to store a lot more, and it can't even really train that well. It's not really mathematically as sound as this. So yeah, that's the algorithm. The main idea is that if you project to a low dimensional space, you only have to, your optimizer states are, your optimizer moments and stuff only work in that low dimensional space, and you can do a good update in that low dimensional space instead of doing that in a higher dimensional space, which allows you to store your low dimensional moments and use a lot less memory because the moments take up a ton of memory. So that's basically the intuition behind this. Unlike LoRa or other techniques which have to have a lot more memory usage, here you just have a lot lower memory usage because you're working in the low dimensional R space. So what do the results look like? And they look quite good. So for a low, they look quite good. So they train it on a GPT model and a BERT model. The GPT model, it does well. So GaLore versus full rank. And since it's storing a lot less memory, you can see here that it does quite well, and it's a lot less memory. It's more memory efficient. Using, and this is different R's, so different sized or different size low rank projections. So yeah, it does quite well compared to the other tasks. This is perplexity here. So lower is better in this case, and it does a lot lower, or it has a lot lower perplexity compared to the other ones. Like just a normal low rank projection does quite bad. LoRa and ReLoRa don't do that well. And yeah, this is pre-training on a llama model. So it can pre-train an entire 7B llama model here. And one thing to note is that it can actually pre-train an entire 7B model on one 4090. So they mentioned that here. The 8-bit GaLore further reduces the optimizer memory, notably demonstrating the first time pre-training a 7B model on a consumer GPU with 24 gigabytes of memory. So quite cool that you can train an entire 7B model and get as good performance as a full rank model with their method. So yeah, quite cool to see that you can do that. 8-bit GaLore, it's very low. The memory usage is a lot lower than say 8-bit Atom, and it does very similar. The results are very similar. So this just shows that you don't need full rank for your gradient. You just need the low rank. They also do it on BERT. So if we go to BERT, they use Roberta for fine tuning, just to show that this thing can also be used for fine tuning. And they show that it does similar performance as LoRa, but it also has lower memory. Not by a lot, but I think this is just to show that they have a lower memory usage and they get better results on fine tuning, which LoRa is really good at. LoRa is really good at fine tuning. So it was made for pre-training, and it can also do quite well at fine tuning. Another thing I wanted to show was the update frequency. So this is our big T. So they show that a small big T and a large big T aren't very good. However, something in the middle, so a big T in the middle is good, so normal trade-off. And that's because if you update too little, then you're not done optimizing that subspace. So that would be here. It's not done optimizing that subspace, so you're changing subspaces too much. So it's not going to basically converge in that subspace. And here, you're not changing subspaces enough, so it may basically converge in a subspace and be done optimizing that part of the subspace, but keep on optimizing that part of the subspace, making it kind of useless because you don't need to update that part of the subspace anymore. So yeah, it's always a trade-off. Other than that, I think that's about it. Pretty cool that they have this mathematically sound algorithm that doesn't have too many that doesn't have too many assumptions, and it works really well. I'm very curious to see how this actually works in practice because it looks like it can work quite well. Though I don't know how the assumption with reversibility is going to work out. I don't know if that's a very hard assumption or not. It doesn't look like it because they use attention, and that was one of the things that they said. I think they said that they didn't prove had reversibility, but maybe it does. Yeah, so that's the algorithm. That is GaLore.